So welcome back to the swinging bar. I just want to talk about a couple of variants that we could have done on this before we do it the easy way, right? Notice if it's not a bar, what's different in this problem? Pretty much just I, as well as where the center of mass is with respect to the axis of rotation, right? So the analysis methodology is the same. The only thing that really changes is what this looks like and what we're putting in here, right? Because all that matters for this problem is how far the center of mass is from the axis of rotation, as well as what is the moment of inertia of the thing that is swinging, right? So we'll see some variants about that that'll make some sense later. But let's make this a lot easier. So how can we do this swinging bar problem a lot simpler? Well, the answer is energy, right? Because every time we've had a complicated thing with a complicated path, and we didn't want to have to deal with things, and there was calculus and changing things, we found that an energy analysis is the way to go. So let's talk about energy for this object. So I think we can clearly see that we have gravitational potential energy becoming kinetic energy. Now, here's the difficult thing about it. When we're dealing with the term Ke is equal to 1/2 mv squared, remember that's KET and that's VCOM. But the problem with talking about translational kinetic energy with a swinging bar is the whole thing is not translating because of this fixed point. Now you may want to argue, oh, but the center of mass is moving. The problem is, remember when we derived Ke rotational being 1/2 I omega squared, we derive that from saying that the kinetic energy rotationally is equal to the sum of each individual little dm's translational kinetic energy. Now we didn't do that integration because it'd be kind of annoying. Instead we just generated this term. So even though the center of mass might be moving at a certain speed, as we demonstrated in the last video, and I'll pull that piece of paper up here, at any given point, different points on the body have different tangential speeds. And so to find out the kinetic energy at any point, if you're using that 1/2 mv squared equation, well, which v are you using and for what mass? And so since each little bit of mass is a different distance away and is moving at a different speed at all times, that's not a really good way of doing it. So for a constrained object that is rotating, we're always going to use this kinetic energy term, not that. If our object is rotating and its center of mass is translating because it's not constrained, like a rolling ball or my soup can, that's chapter 11, and we'll deal with that later. So if it is an energy problem, well, let's treat it like an energy problem. The first thing to do is talk about sort of like positions, right? So I've drawn it. Actually, let's do potential energy. So here's the thing. How do we deal with potential energy with extended bodies? Well, very simply, that we only consider where the center of mass position is of that object. So let's once again assume that this thing is a uniform density. So I can say, well, not uniform density. So I can say the center of mass is at the geographical center of it. So here we go. So now what I'm going to do is pick a UG is equal to 0 line. There are two good places to choose. I could either choose just the initial position or I could choose the final position. I'm going to choose the initial position just because I tend to like to do that. So there's UG is equal to 0, right? So let's call this position A and this position B. And the reason why I want to call it A and B and not initial and final is because we're going to look at an intermediary position C in a couple of minutes, and I don't want to have like an initial, final nonsense. So here we go. So if we're looking at the energy at position A, well, it's at rest, and it's at the UG is equal to 0 line, done, 0. Energy at B, well, it's not at the UG is equal to 0 line, so I've got to say there's a UG term, and we know that it is also rotating. So we're going to have a kinetic rotational term at position B. So now, are the energies equal? Well, one might say, what about this pivot force? Well, very simply there, the pivot forces here, even though they exist and are non-conservative, they're not going to do work because this point is not moving. So the energy at A is equal to the energy at B because the work done by non-conservative force is equal to 0. So now I have 0 is equal to, let's fill this in, I've got mg. Well, where is that position? Well, we know that this center of mass is L over 2 because it's uniform density. So with respect to this, it's got to be negative L over 2 because it's below the UG is equal to 0 line by half the length, plus 1/2 I, which we know is a bar about its end, so 1/3 ml squared, and then omega at position B squared. So looking at that, the masses cancel, so nice. One of the L's cancel. You can see that this 2 and this 2 cancel. Let's clean it up. I'm going to bring this over to the other side. So I've got G is equal to 1/3 L. It looks like omega B squared, or omega B is equal to plus or minus 3G over L. So cool. That's the same result that I got here, but I didn't have to do all of that. Oh my God, look how simple that is. It's 3 lines of work after the premise. Yeah, I think we kind of like, we like this analysis a lot better. So let's look at an intermediary position, boom, right? So let's say that's a certain theta downward. So once again, what we have to do is just track where is that position. So in other words, I need to know what that distance there is. Well, if that's L over 2, this is just merely negative L over 2 sine of theta. And so instead of putting in negative L over 2, I'd just be putting in negative L over 2 sine theta in there, and then the analysis would be the same. And so just by parallelism, I think you can see it just be radical 3G over L sine theta, pretty simple and straightforward there. And so the swinging bar problem is super easy with conservation of energy. And remember, we're not using kinematics once again because the acceleration is not uniform. So how does this look different if the object is not a bar or the bar is not swinging about the end? Once again, it's all about what is I, and it's all about what is here in this term, is where is the center of mass with respect to your UG is equal to 0 line at the point that I care about it. Right? Once again, I could have the UG is equal to 0 line where the center of mass is at the end. That just swings this entire term over to here. Doesn't really change the analysis all that much. And then this thing's initial Y position is positive. But that's pretty much all of the variance with this. The last video that we have for the swinging bar problem is going to entirely focus on what's going on at the pivot.